The standard model of cosmology, known as lambda CDM, describes a universe composed mostly of dark energy and cold dark matter, governed by general relativity. The lambda in that title refers specifically to the cosmological constant. This model assumes dark energy is an unvarying, intrinsic property of the vacuum of space. Mathematically, it is defined by an equation of state where the parameter W is exactly equal to -1. This graph tracks the scale factor of the universe over time. Under the assumption that W equals -1, the dark energy density remains constant as volume increases. The macroscopic consequence is a universe that expands exponentially, asymptoting toward a cold, infinite de Sitter space. Over a long enough timeline, this expansion isolates every galaxy structure. Stars burn out, black holes evaporate, and entropy reaches maximum. The universe arrives at heat death, a state where no usable thermodynamic work can be extracted. However, this timeline depends entirely on the assumption of a static vacuum. If W deviates from -1, the prediction of eternal expansion and thermal death is invalidated. To test the assumption of a static vacuum, cosmologists require observational data across massive scales of space and time. This is the primary objective of the Dark Energy Survey's Year 6 release. Using the Dark Energy camera, researchers compiled a precise photometric dataset capturing 150 million source galaxies across 5,000 square degrees of the southern sky. The survey employed a 3x2-point analysis methodology. By measuring cosmic shear, galaxy clustering, and galaxy-galaxy lensing simultaneously, the team mapped both the growth of massive structures and the geometric expansion of the universe over billions of years. We can model a changing dark energy density using an evolving equation of state. Here, W is defined by W0, the current state, and WA, which measures its evolution as the scale factor changes. Combined with primary cosmic microwave background data, DES Year 6 parameters settle at W0 -0.82 and WA -0.63. A true cosmological constant sits at -1 and 0. Instead, the data reveals a 3 sigma deviation from that static baseline. A negative WA combined with a W0 greater than -1 translates to a dynamical dark energy field. It indicates that the energy density of the vacuum is shifting over cosmic time. Because observational data reveals a preference for an evolving vacuum, we must look to particle physics for mechanisms that allow empty space to change states. To physically halt and reverse cosmic expansion, a mechanism must exist that is capable of shifting the universe's vacuum energy from a positive value to a negative one. We find that mechanism in the standard model of particle physics. Specifically, we look to the Higgs field, settling into our current electroweak vacuum state of 246 giga-electronvolts shortly after the Big Bang. The stability of this vacuum is determined by the masses of the particles that interact with it. Current collider measurements place the mass of the Higgs boson at roughly 125 giga-electronvolts and the top quark at approximately 173 giga-electronvolts. The ratio of these two masses places our universe in a metastable condition. We do not reside in the lowest possible energy state, but in a local minimum known as a false vacuum. Our universe sits in a local minimum, the false vacuum, separated by a massive energy barrier from a deeper negative energy true vacuum. Through quantum tunneling, a localized region can pass directly through this barrier into the true vacuum state. This is false vacuum decay. The immediate result is the nucleation of a true vacuum bubble. The walls of this bubble expand outward at nearly the speed of light. The standard model provides a physical pathway for this transition. Current mass measurements point to a quantum trigger capable of altering the vacuum energy density on a cosmic scale. Inside that expanding true vacuum bubble, the physics of our universe are entirely overwritten. The new value of the Higgs field instantly alters the masses of elementary particles and the strengths of the fundamental forces. Looking at the Friedmann acceleration equation here, we see how this alters the macromechanics of the universe. The stress-energy tensor updates, and the cosmological constant term shifts to a negative value. A negative vacuum energy ceases to drive the expansion of space, acting instead as an overwhelming gravitational force pulling inward. Graphing this kinematic shift, the acceleration of the scale factor becomes negative. the universe halts its expansion, turns around, and initiates a universal contraction. As the collapse accelerates, the immense latent energy stored in the old false vacuum is liberated. The bubble interior is subjected to intense heat, annihilating all existing atomic structures and chemical bonds. The matter inside the contracting universe is reduced to a uniform, hyper-energetic plasma as space-time rapidly rushes toward a big crunch. This phase transition effectively resets the baseline of cosmic entropy by destroying high-entropy structures and flooding the volume with vast amounts of free energy. Classical general relativity predicts that this contraction will end in a central singularity of infinite density, a mathematical point where all physical laws break down. However, classical gravity does not account for quantum mechanics. To resolve the singularity, we apply the framework of loop quantum cosmology. This visualization represents spacetime under loop quantum cosmology. Space is not a smooth, infinitely compressible continuum. It is quantized into discrete, interconnected loops. There is an absolute minimum limit to volume, defined by the Planck scale. As the universe compresses the hyperenergetic plasma, it forces matter toward this maximum density limit. Hitting the absolute geometric limit of the loops triggers a quantum mechanical reaction. The spacetime quanta exert an immense repulsive pressure against the incoming mass. This moment of reversal is the Big Bounce. Instead of collapsing into an infinitely dense singularity, a quantum gravitational buffer forces the contracting matter and energy outward with immense repulsive pressure. Immediately following this bounce, the universe expands rapidly. It is a hot, dense, low-entropy environment, conditions mathematically identical to the Big Bang. The DES Year 6 results suggest a preference for a dynamical vacuum. When paired with the metastability of the Higgs field, these findings provide a measurable pathway from expansion to contraction, and eventually a new cosmic cycle.